This is the MAMMOTH Rover, or the Mars Analog Multi-Mode Traverse Hybrid Rover. The MAMMOTH Rover is being used to research new ways to increase the mobility of planetary rovers. It is a novel platform in that it can reconfigure its pose-to-point sensors or stabilize its payload. It can change its footprint to maintain static stability, as well as fit into small spaces or between obstacles. It can even clamber out of soft soil or over an obstacle. This over-actuation also makes it susceptible to instabilities in certain poses. The MAMMOTH Rover has this enhanced mobility given its 16 actuators. The rover has to figure out which poses are suitable to traverse terrain efficiently while staying safe. These unique challenges require complicated guidance, navigation, and control software. To develop this software in a simplified and streamlined manner, we have chosen a model-based software design scheme provided by MATLAB Simulink. The Simulink model used to develop GNC for the MAMMOTH Rover includes models for a motion controller, a motion planner, a path follower, an interface to the robotic hardware and an interface to a simulation of the rover, sensor data logging, rover visualization, and sensor data plotting. To demonstrate our development process using Simulink, we will summarize the implementation of an example motion control task called actively articulated suspension. The objective is to get Mammoth to localize itself and perceive the terrain around it using an RGBD sensor mounted on top of its head. The vehicle operator then gives the rover a desired forward velocity. The vehicle must maintain this velocity while keeping a constant pose by actuating its legs and conforming to the terrain. To interface the RGBD sensor, we use the Robotics Operating System, or ROS, which we then interface with Simulink using the Simulink Robotics System toolbox. To move the vehicle, an operator updates constant blocks within the user interface model. To test the actively articulated suspension, we first run a simulation of the robot. The simulation shows a kinematic skeleton of the vehicle moving over a rolling terrain. It can be seen from the green wheel contact point tracks and the red body track that the vehicle is keeping its posture while moving forward and actively conforming to the terrain. The next stage in testing is to run the control scheme on the actual vehicle. The hardware interface model sends desired actuator rates and receives vehicle sensor data via TCP and UDP blocks over the rover's local area network. The interface between the simulation and the hardware-in-the-loop blocks are the same, allowing for rapid design iteration and testing in both realities. We now run the model with the hardware interface activated. The first wheel is raised to follow the contour of the obstacle. Followed by the second wheel. And the rover completes its traverse over the obstacle while maintaining its posture. A waypoint follower has also been developed so that the vehicle can autonomously follow a path. The rover operator can tell the MAMMOTH Rover to dig a trench between waypoints. The vehicle digs a trench by driving its back wheel in the opposite direction to its other wheels. The waypoint follower control model is duplicated and included in another Simulink model used to control a completely different rover called Mawson. Using the power of model-based software development, it is our aim to produce guidance, navigation, and control methods that will one day be used to explore the surface of Mars. Until then, from all of us humans and robots at the Mars Yard, farewell.